CH3Cl is going to look something like this, and it's going to have a dipole moment pointing towards the more electronegative atom, which is chlorine in this case. So it's going to look like this. So we know that is a dipole moment that's going to have. Now, so that can't be one of the answers. Then the next molecule will look like this. And even though it might appear like it's a linear molecule, so the dipole moments, which will point towards the electronegative atom, if it wasn't drawn like this, it would look linear and it would look like it'll cancel out. But we know since the oxygen atom has two lone pairs, it's actually gonna have a bent geometry. So overall, the dipole moment's gonna point up. The net dipole moment will point up rather than cancel out. So it does have a dipole moment. Our next molecule will look like this. With the two chlorine atoms and two H atoms. And once again, the dipole moment is going to go towards the more electronegative chlorine relative to the carbon. So there's going to be a net dipole moment going up. So lastly, and if you went through this and you saw that these three, or maybe one of them, you're like, oh, I'm not sure, and you went all the way to the end, you'll see that the carbon is going to have a tetrahedral shape because it's a sp3 carbon, because it has the steric number 4. So it actually look more like this. And all the dipole moments will actually cancel out. So it won't have a net dipole moment all around in the molecule, leaving that as the answer. Any questions about anything that happened there? Okay, so next question. So the following compounds all have the similar molecular weights, which has the highest boiling point. So when we're looking for anything boiling point related, especially when the molecular weights are similar, we already think of looking at what type of bonding is going on force-wise. So if you're not comfortable looking at molecules through this type of structure, you could always draw them out so it's more clearly seen. And you can also see the functional groups more easily. So we know this is an aldehyde. Our next molecule would be an alcohol. Then we'll have an ether. Alcohol. Then we'll have an ether, and then lastly, an alkane. Once you see the OH, you know that in the alcohol, in B, you know that there's hydrogen bonding going on. So it'll have the highest boiling point, opposed to none of the other molecules or functional groups have this hydrogen bonding going on, and hydrogen bonding molecules have the higher boiling points force-wise. Good? Now, in the following reaction, this doesn't really look familiar as the type of reaction that we've seen, but in fact, this actually would be classified as an addition reaction, because addition reaction is characterized by the breaking of a pi bond and the creating or forming of two new sigma bonds. And here, if you see in comparison to the starting materials to the end materials, here we have a pi bond that breaks in the starting material. And at the end, we have the formation of a sigma bond here of the OH. That's a sigma bond being formed. And then a sigma bond of the carbon, of the two carbons. So we have one pi bond that broke and two sigma bonds that were created. So if you ever need to go to like the basis of what addition and substitution elimination are, remember that's what really characterizes addition: the breaking of a pi bond and the forming of two new sigma bonds. Okay, so here we have a graph, which sometimes scares people, but it's okay. So in the question they're asking which of the descriptions from A to D correctly describes the following energy diagram. So the first thing I always like to look for is how is the energy changing from the reactants to the products. And here, even though it's a very small change, it still is a small positive change because the products have more energy than the reactants, which is the characteristic of an endothermic reaction. So this is gonna first of all tell us endothermic, and by doing that, we've already eliminated two options, which are the two exothermic options, and then all we have to distinguish now is which of the two steps is the activation energy. So we know the top of the hump is showing a transition state, as well as this middle part is the intermediate. Now, in this problem, the activation energy is going to be the X part, should be the first step, the first transition state, because it has the lower activation energy relative to the intermediate. So everyone's cool with that? Okay. So moving on. So actually for problem number 5, after the review was submitted, a more relevant question dealing with deuterium was found. 2 more relevant questions. So we are not going to cover that problem that is in the actual review because it's not as appropriate opposed to these. So if you want, I'll give you a second to copy this down. So then we can go over it. You don't have to worry about writing it as I'm talking about it. And I want you to note that this is D, which stands for deuterium. Okay, so this problem is asking what the major elimination product is. So first off, we'll look at what type of base we're dealing with. And our base is not a bulky base, so we know our product is more than likely going to be the more substituted product. So this is non-bulky. So we'll have a more. But aside from that, first off, on an E2 elimination, we have to make sure that our transition state conformation is one that has the beta hydrogen atom and the leaving group in an anti position, and specifically trans and diaxial to each other. So I'll go ahead and write that down because that's a bit of information. So we have to have the beta hydrogen and leaving group anti to each other, which in this case, when you're dealing with a chair conformation, means trans and diaxial. So here, if bromine is our leaving group, right now, to start off with, we already know that in this conformation, the elimination product can't even proceed because our bromine is in an equatorial position and not in an axial position. So to get our bromine to an axial position, to then see how it's relative to a hydrogen, we're gonna go ahead and do a ring flip. So when we do the ring flip, now our bromine still remains up, if you notice, but now it's just axial. And it's gonna have a down hydrogen. Then our methyl group is gonna become axial as well and still point down. It's hydrogen. And then our deuterium is gonna become equatorial if our hydrogen axial. So of the two hydrogens that are in the beta position relative to the carbon with the leaving group, we see that only an elimination reaction can happen with this hydrogen because this hydrogen is still not diaxial to the bromine and it's not trans. So our product in a non-chair conformation, so you could either look, it could either say like, this is the type of conformation that the product will have to be in, or if it actually wants the elimination product, then it will look like this. With the deuterium still on, and the methyl group in that position. Any questions? Okay. So then, down here, this is asking what is the product of the reaction sequence, and once again, we're using deuterium in place of hydrogen. So immediately though, you should probably recognize that this is a hydroboration oxidation because it looks very similar to what we would be using, the reagents we would be using in a hydroboration oxidation, which usually are BH3, THF in H2O2, and AOH. So for this product, because now we're introducing a deuterium to our product rather than hydrogen, it's important to know what the stereochemistry and regiochemistry are of a hydroboration oxidation reaction. So we know our regiochemistry, which I'll use RC to abbreviate, is going to be the anti-Markovnikov, which I'll just put anti-Mark. And our stereochemistry, even though the H2O, which is what's going to get added, or in this case, the DTO, which is going to get added across the double bonds, can be added on any side, it still needs to be added in a syn addition to the bonds. But because it could go on any side, it's going to be a race mixture. So that means we still will have an enantiomer. So in this case, if we know we want both the deuterium and the OH added on the same side, our product's gonna look like this. The OH will be on the less substituted position. And over here, the methyl is gonna face down with the hydrogen so that the deuterium can face up with the OH group. And because it is a race mixture, it's going to have its enantiomer with it. So, is everybody good with this question? Any questions? The what? So, so at the end, if I have time, then I'll go back to that of drawing the mechanism, because since it's specifically asked for the product, so just remind me. Or at least I'll attempt. Okay. So then going back to that's the only changes that will be in the study guide. So then, for problem number 6, which is dealing with significant resonance structures, to check how many significant resonance structures there are, especially if you're not too comfortable with resonance structures, a key or a trick is just picking up what the common resonance structure arrows are. So here, for instance, in the structure that we're given, we have a allylic positive charge relative to the pi bond. So we know that we can use an arrow to push this pi bond over to the positive charge. I'm going to push the pi bond because this is an allylic positive charge. So then our next resonance structure will look something like this, with now the positive charge on a carbon. Now again, we see, and there will be 2 oxygens on here, which might not always be drawn out for you. So again, here we see that there's a positive charge adjacent to a lone pair. But like I said, if those lone pairs weren't drawn, you have to remember that a neutral oxygen will have those 2 lone pairs on it. So here, we have a positive charge adjacent to a lone pair. So this lone pair could be pushed over there, and we create a pi bond from the lone pair. Now, here we still will have we can still make another, actually the product of, the resulting resonance structure from pushing this bond over there will look like this, with the positive charge now on the oxygen, and there's still another lone pair on there. And then that'll be the end of how many resonance structures for this compound with the positive charge on the oxygen, because we don't recognize any other resonance I can't think of that word now. Tricks, I guess you could say. Patterns, there we go. We don't recognize any other resonance structure patterns. So then this will be a total of 3 resonance structures, because you still have to consider the first one. So, moving on. This problem is specifically asking how many sigma bonds are present in the following compound. So, some reminders of what characterizes a sigma bond is a sigma bond includes the CH single bond. So each CH single bond would equal one sigma bond, as well as one of the bonds of the CC double bond, because one is a sigma bond and the other is a pi bond, and an OH bond is a sigma bond, and carbon-carbon bonds are sigma bonds. So with that said, when you count this all through, I'm gonna start with first counting the carbon-carbon bonds just to keep everything together. Oh, and actually as well, a carbon-oxygen bond in this compound we see includes a sigma bond. So here we have 1, 2, 3, 4, 5 carbon-carbon bonds. Then we have 1 carbon-oxygen bond, 2 sigma bonds from the CC double bonds, and then 1 from the OH, and then lastly you'll count on all the CH bonds. So that would be 1, 2 here, 3, 4, 5, 6, 7, 8, 9 CH bonds, which will total up to 18. 8. Total sigma bonds. Opposed to this extra pi bonds would just be 2. Okay. So next problem is asking what would be the most stable chair conformation of trans 4-terp-butyl-cyclohexanol. So first off, I'll go ahead and draw the trans 4-terp-butyl-cyclohexanol in the familiar we're most comfortable with, which for me is the bond line structure. So I know since it's trans and since it's a hexanol, my OH starts at wherever I decide is 1. Then, so 1, 2, 3, 4. 4 would be my terp-butyl group, which, once again, this is a trans cyclomolecule. So my terp-butyl group is going to be on a dash as opposed to a bond, a wedge. So when I put this in a chair conformation, it looks something like this. My OH here, going up. These would be H's. I still have a hydrogen up here, and then a hydrogen down, and then until finally I get to my terp-butyl group, which is on the 4th carbon. 1, 2, 3, 4. And it's facing down, so I'm going to have it on an actual group down. Now, this is asking, though, for the most stable chair conformation, and axial positions are less stable than equatorial positions. So ideally, we want to have all of our substituents on equatorial positions. So then we'll do another ring flip to show that. So that would look like this. Now I have my terp-butyl group axial, and this is 4, 3, 1. Counted backwards there. and equatorial, and my OH group as well, equatorial. And it's important to still note the reason why you have to go ahead and check in a chair conformation. If you're good at putting it straight to equatorial, that's fine. But more importantly, you have to make sure that when you're going from this to the chair conformation, that they're still gonna remain trans. So in this case, they were both able to still stay trans while converting to being equatorial, but there might be a case where only one of the groups could be on the equatorial position, and in that case, you have to check what would create the less steric hindrance for the most stable. So for this answer, it's going to be A, the OH group equatorial and terp-butyl group equatorial. As well, you have to make sure that the actual groups can both be equatorial, because they could give you this answer. If you just read it, you know if they're both in the equatorial position, that's going to be more stable. But if it's not possible because this would still end up being up, which would make it cis, then it would not be the correct answer. That could be like a trick question. Okay, so now we're moving on to question number 9, which is converting bond line structures to Fischer projections. So there's different ways to convert a bond line structure to a Fischer projection, so I'm going to try and go over both of the ways. For myself, I like converting the Fischer projection into the backbone and then turning the molecule. So when you do that, first off, note that an ethyl group signifies CH3, CH2, so you don't get your carbon numbers mixed up, and a methyl group is CH3. So when I do my little backbone, and if any of you ever use the second language book, this is the method that I'm going through right now, in which they go ahead and, this is a black pen, they create a backbone type picture with my R group down here, and then it starts the top of the backbone with my OH group now, because it's on the right side, and my H group here. And then I want to remain with everything on the same side, so this would be my H here, my OH here, and then my OH would be here with my H on this side, and then my other R group, which is methyl, would be here. And then when you convert this to a bond line structure with this same shape, it will look more like this, with my ethyl here, my OH on a dash, my next OH on a wedge, and then my last OH on a dash. But you'll never get an answer that looks like this, most likely. They'll want you to turn it, and once I turn it, what it'll finally look like is this, with my OH on the dash. My OH doesn't get turned because it's already in the position I want it to, and this, by the way, represents the ethyl group, CH3, CH2. Then this OH group would have to flip, so now it would be on a dash, and then my last OH group is okay. I don't have to turn it because that's going to stay on a dash. Now, this way is only really good if you're a visual person, and if you're not comfortable with going about this way, especially when you have a multiple choice test that you could play around with a little bit, then the best bet is to take the configurations of the chiral centers and compare it to the answers. So when I do that, and that's also a good way to just check yourself, period. When I take the configuration of these chiral centers, in my first carbon, my oxygen is gonna have first priority, then this group down here will get second, my ethyl third, and then my hydrogen fourth. but my hydrogen is on a wedge because that's what the Fischer projection tells us, that anything horizontal is on a wedge and anything vertical is on a dash. So when I take the configuration of this, even though 1, 2, and 3 are going clockwise, I have to flip it to S because my H is on a wedge. So rather than S, even though the 1, 2, 3 are clockwise, rather than R, because the 1, 2, 3 are clockwise, it's going to be S because my H is on a wedge. Then when I do my next one, so over here, I know this carbon is S. And when you compare it, it's the same case. My OH would be my first priority, this would be my second, this my third with my H on a dash. So it's R, but it gets flipped to S. So that's already how we check that the first one is correct. Then for the next molecule, for the next chiral center, this is gonna get first priority. And now between the top and bottom, the top will have the higher priority. So it's gonna be 2 once again. Well, this number, I'm just gonna recycle it, but now this side is gonna be 2 because it has the one more carbon. So even though they both have the oxygens at the same position, when you go even further down, this is gonna have an extra carbon opposed to the methyl group attached to it. So that's the point of difference. So that's 1, 2, 3, and again my hydrogen 4, but it's gonna be on a wedge. So once again, even though my 1, 2, and 3 are going clockwise, so which would make it R, it has to be flipped to S because my H is on a wedge. And this is going to be the case with all of everything in this Fischer projection because all of the H's are on a wedge, as you can see. And then when you check it here, if this has first priority, second, third, it'll be going clockwise, but with my H on a wedge, it gets flipped, so it's S as well. And then lastly, this will get first. This would have second because of the oxygen connected to that carbon. This will be third, and this will be fourth. So in this chiral center, it's going anti-clockwise, counterclockwise. But because the H is on a wedge, it's going to be R, as in the same case in this molecule. So you could do either of 2 ways. You could go ahead and take the configurations and just make the molecule as you go with the configurations, but making sure you have it the correct ways. Or you could do the backbone, drawing the backbone, and then knowing where you need to flip, where it's appropriate to turn the carbons. Yes. Because the Fischer projection is characterized by anything on a vertical bond anything on a horizontal bond is a wedge. So unless they gave you a Fischer projection and they happen to be really nice and do this and give you the H up here, maybe make it look something like this as opposed to so if the Fischer projection looks something like that, then the H happens to be on a dash now, but they usually don't give it to you like that. They usually give it to you with the H on the right side. Or, yeah, on one of the sides. Okay. So now, in the next problem, this is dealing with heats of hydrogenation, and it's asking for the greatest heat of hydrogenation. So, heat of hydrogenation has to deal with energy. So if it's greater, that means it's going to be a less stable molecule because energy and stability are opposite of each other. So when something has more energy, it's less stable, and when something has less energy, it's more stable. So just as well, if they're asking for lowest heat of hydrogenation, then you would be looking for the more stable products. I just wanted you to note that, just in case. but in this case, we are looking for the greater one. So first, since we're dealing with alkenes, we'll look at how substituted the alkenes are. So in the first case, we have 3 substituents relative to the double bond. So it'll be tri-substituted. Here we have 2. So this is di-substituted. Next we have 4, so this is tetra-substituted. And lastly, we have 3. Let's try substituted. So for this problem, since, like I said, we're looking for the greatest heat of hydrogenation, the more substituted an alkene is, the more stable. More stable. So we're looking for the less substituted alkene, because that'll be the less substituted one, the less stable one, which would be B. But just as likely, if they were asking which of these alkenes has the lowest heat of hydrogenation, then we'll say the tetra-substituted one. Now we'll be looking at the relationship between this compound. So this is given to us in a Newman projection, which could sometimes be a little tricky to make sure you're looking at the correct thing. So there's 2 ways you could approach this problem. One would be just counting the carbons, but not really worrying about the order of the carbons, just knowing how many carbons are there. So for instance, I know here I have 1 carbon, then I have the carbon in the back because the Newman projection is characterized by showing 2 carbons connected to each other. So I have that second carbon in the back, then 3, 4, 5. So when I draw this out, I'll have my CH3 back, so that's my CH3, then my second carbon that I found, 3rd, 4th, and 5th, and then connected to my 3rd carbon, I have this isopropyl group. So it looks something like this. But now we know that we're going to have to redo the numbering to make sure we get the correct name of it. And that's the best way when you're looking at relationship between compounds to make sure you don't get the wrong answer, is ensuring that the compounds have the same name. So when I'm naming this carbon, I'll look for the longest parent chain, which would be here 1, the longest parent chain with the most substituents, by the way. So this will be 3, 4, 5. I did it going this way rather than 1, 2, 3, 4, 5 as I started, because that'll give me 1 substituent, as opposed to here where I'll get 2 substituents. So the name of this compound would be 3-ethyl, because this is an ethyl group, 2-methyl, and then my parent chain is 5, and I have and it's saturated, so it'll be pentane. Now, if we did the same for the next Newman projection, then once again here I have 1 carbon, then on the back 2, 3, 4, 5. So when I draw this out again, on my back carbon, I have not only this group on the right, there's also a methyl group connected to the second carbon back there. So I have to draw that out. And then on my 3rd carbon, I have this chain, this ethyl chain here, which you could already immediately see from from having the methyl and ethyl chain, it's most likely going to be the same compound, because when we number it again, 1, 2, 3, 4, 5. This ends up being the same case with the 2 on the methyl and the 3 on the ethyl group. So I'll have and the ethyl on the 3rd carbon. So it would have the same name. and it would be the same compound. So that would be its relationship. Okay. So moving on. This is more like classifications of reactions. So in this first reaction, we have, immediately we see we have a nucleophile because we have the lone pair and the negative charge. And we have an alcohalide on this side, which is a primary alcohalide. So, and compared to from our starting material to our end material, we see that this bromine is actually getting replaced because this nucleophile is going to attack this carbon as the bromine leaves, which is a characteristic of a substitution reaction. And more specifically, an SN2, because it is a primary substrate, we know it's going to go through an SN2 mechanism, which is why I drew the nucleophile attacking and the leaving group leaving at the same time. Now, in the next problem, this is going to be an elimination reaction because we're forming the 2 pi bonds from our leaving groups leaving. So but it's going to be 2 E2 reactions that succeed each other. And one thing I want to note is for this reagents that you could use for this, even though it's not asking, for this problem, you could use the reagent you'll most likely see being used is the excess sodium amide in liquid ammonia, which is NaNH2, and then NH3, followed by water. They use this so that the 2 elimination reactions could happen at the same time, like in the same capsule, you could say. But if you wanted to, for the first elimination reaction, that you get to form the first bond, that the first leaving group and hydrogen leave, you could actually use any strong base. So you could even use as long as it doesn't compete with a SN2 reaction. So like NaOT you might see being used. It's the second elimination reaction that is imperative that very strong base of of sodium amide is used so that you can form the alkanite ion that can then be protonated by the H2O. So either of these mechanisms would work, just going straight from here to the with excess to form the triple bonds, or using a different strong base and then making sure you use this base after to form the triple bonds. Okay. So now we're gonna do IUPAC naming practice. So, is there any questions about that last question? Okay. So here, immediately, this is going to be a diene because we have 2 double bonds. So I like to characterize what type of functional group I'm working with. So this will be a diene, and when we count it, we want to have the bonds with the lowest numbers, but either side we start from would be, they'll end up with 3 and 5. So we start from here, 1, 2, 3, 4, 5. The same here, 1, 2, 3, 4, 5. But we're gonna start from the left side so that the fluorine gets a smaller number. So this will be 1, 2, 3, 4, 5, 6, 7, 8. So this is going to give us the parent chain is going to be octa, and our double bonds are going to be at 3 and 5, with our fluoro group at the 3. Now, the one important thing that we're missing here is including the stereoisomerism, which we have 2 double bonds, and we could actually account for the stereoisomerism for both of these double bonds by using the E and Z technique opposed to cis and trans. So here, our fluorine is going to have highest priority in the first double bond that we look at. Our fluorine will have highest priority on the left side because using the Cahn-Ingold pre-log rules, we go by the higher atomic number when assigning priority. And then on this side, it's going to be the bottom. So they're both on the same side. So Z is for Zane side. So this would be, this would be 3Z. And then for 5, the double bond at 5, we compare, once again, the 2 groups connected, and here we're going to have the higher priority groups are going to be on opposite sides. So this would be E. So 5E. So important things like in this problem, we're making sure if you could account for the stereoisomerism of both double bonds, you go ahead and do so, and not forgetting the di-ene part, because the di is signifying that there's 2 double bonds in the molecule, in the compound. Next, this is a bicyclo system. So we'll start off with numbering from going around the longest ring, which in this case is going to be the left side. So we'll start here at this bridgehead because this bridgehead has a substituent on it opposed to the bottom bridgehead. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're gonna, and there's no, it's saturated. It is saturated. So it's gonna be nonane. And then when we're looking at what numbers to put for our bridgeheads, on this side of the bicyclic system, we have 4 carbons, 1, 2, 3, 4. On this side, we have 1, 2, 3. And then in the middle, 0. Then you put the bicyclo part. And then we have a methyl group at 8 and an ethyl group at 1. And we have to make sure it's in alphabetical order when naming it when putting it in the name. So we'll have 1 ethyl, 8 methyl, which, sorry, that got really small in there. But so the final name would be 1 ethyl, 8 methyl bicyclo 430 nonane. Now, for this molecule, we immediately see that it's based off of a chiral center, but it's still asking for the whole IUPAC name. So we have to go further than just giving it configuration. We have to name the full molecule. So to start off with, I'll look at what functional groups are presented. So we have a double bond and we have an alcohol group. And an alcohol is going to take over the functional name because it has the highest priority. So our suffix is going to be OL. So when we have an alcohol group present, we want to start numbering the compound from the side that will give the alcohol the smallest number. So we'll start from this side. because we see this carbon is right next to this OH. And we can't start from this carbon because that wouldn't be the longest parent chain. So this will give us 1, 2, 3, 4. So that's gonna be, we'll put note that our alcohol starting at 2, and 4 carbons represents a butane group. So our family name, our parent chain will be butane. Then we still, in this problem now, we do have saturation, which is shown with the En. So we have to account for that. So here, our double bond starts at 3. So you're gonna note the 3 for the double bonds before the butane. And this could also be seen like this. Oh my gosh. I never write it that other way, sorry. But 3N2O. With the 3 right before the representing the unsaturation. Now we still have a bromo group which is connected to the second carbon. So that will be shown here. But now the most important part probably of this molecule is making sure to get the configuration down. So you have at least that part down of the molecule. Now we have to figure out whether it's S or R at the chiral center. So here, our highest priority is going to go to the bromine because it has the higher atomic number. And once again, to reiterate, when using the count and gold prelog rules, when you're assigning priority, you do it according to the number of atoms, the atomic number of the atoms closest to the chiral or stereo center. So the bromine will get 1, the oxygen will get 2, then this carbon would get 3, and this carbon will get 4. Now here, our lowest priority group is not on a bond, on a wedge or dash, and we need to have it on a wedge or dash to know what it's to take the configuration of it. So there's 2 ways you could do this. If you're good with visualizing, you could go ahead and redraw the molecule so that the methyl group is on the back, in this case, which is the lowest priority, is on the back, which would look like this. CH3, and then now my double bond is back here, my OH is here, and my bromine is here. So then once we do the configuration again, the priority is 1, 2, 3, 4, and it's going counterclockwise, and our lowest priority group is already on the dash, so it'll be S. Or if you're not comfortable with making sure when you're doing this you're not altering the configuration, one of the tricks with configuration is just switching whatever is on the dash with the lowest priority. So I'll go ahead and put 4 here now, and 1 here. So now when I do the configuration with these numbers into account, and when I look at the rotation of it, you're gonna see that it's going clockwise, which is R, but you have to flip it because you just changed it, so it'd be really S. So then the final name would be S2-bromo 3-butane 2O. Any questions? And just a reminder, if you're not here for the session, then you can leave. Now, going on to part D of this problem. This is once again a Fischer projection. I mean, not a Fischer projection, a Newman projection. So, and it's actually a really simple Newman projection. It's just once again being comfortable with knowing those two carbons that are connected in the Newman projection. So when you see this and you remember that there's a carbon in the back and all the other things attached are H, it's 1, 2, 3, 4, 5, 6, which would look like this. 1, 2, 3, 4, 5, 6, and it's just hexane. So I was like really to the point. Now we're gonna go through some synthesis problems. So here we have a ketone that's getting converted to an alkene. So we know there's a few ways to get to an alkene, especially if you're going through like a retrosynthetic analysis. And we actually can go from an OH to an alkene, as well as it's really simple to go from a ketone to an alcohol. And to do so, first, to convert the ketone to the alcohol, you need to do a reduction. You'll need to use a reduction reagent to accomplish this, such as lithium aluminum hydride, which is LAH. Or in this case, you could even use sodium borohydride. So this will give us our alcohol. And we don't finish it off with H2O because we want to get it to that alkene. And to get to an alkene, through dehydration, we need acidic conditions. So we want to dehydrate this alcohol now to get to the alkene. That's an E1 mechanism. And you're going to need a concentrated acid such as sulfuric acid and heat. And this gets us from a ketone to an alkene really simple, rather than converting the alcohol to a good leaving group and then going through unnecessary steps. This would be the most efficient. So there might be other synthesis ways, but this is definitely the most efficient way. Now, for our next problem, so we're not having a change of functional groups, but we're definitely having a change of our carbon skeleton. So here, our carbon skeleton changes. Which, those are the two questions you always have to ask yourself in a synthesis problem. How's my functional group changing, and how's my carbon skeleton changing? So here, we're gonna have we're adding a methyl group to this alkane, but it's still remaining an alkane. And as we know, an alkane is not very reactive, so we're gonna have to introduce a functional group into our alkane. Before anything, as soon as you see just a regular alkane, you know you have to introduce a functional group, and we're gonna do so with bromination with lighter and heat. And because this is a more selective reagent, the bromine is going to get added to where the methyl group is, because that'll give us the most stable product. So to get from there, I always like to do that step first, but when you're doing these synthesis problems, you don't only have to go through a retrosynthetic way, or you don't only have to go through going forward. You could go through and connect the pieces in the middle. So doing the same process, like looking back here, I know if I'm having that double bond, if I'm having these two groups added, I more than likely had a double bond in the middle of that. And to form and to get from, when we know a reagent that could get us from having an alkene to an alkane, which is going to be H2 and PT, because that'll completely reduce our product. So already you know somewhat what the beginning looks like and somewhat what the end looks like. So I already feel comfortable enough to keep going through my problem going forward to get to something like this. So now this is when I just continue going from the beginning, rather than just knowing I'm going to an empty alkane. So if I'm getting a methyl group added to a different position, I'm probably going to have to form a double bond to add on that side. So I'm going to want an elimination. To occur to form a double bond. I'm going to want it in the more, I want the more substituted product. So I'm going to use a strong, non-bulky base, such as NaOMe, which is sodium methoxide. So from here, if I want to, I'm going to need some type of, if my methyl group is on this side, and I'm going to need to form in some way a carbon-carbon bond, which more than likely means I'm using a Gregor reagent, I know I'm going towards creating a ketone, because that's how I'm going to need my Gregor reagent. So to get there, first though, I'm going to probably need an alcohol. Which I could form in an anti-Markinov addition through hydrogenation oxidation. Which my reagents for that would be BH3, THF, H2O2, and NaOH. Now from here, from my alcohol, to get that ketone that I'm looking for so that I could go ahead and add that carbon-carbon bond, I could use chromic acid to do an oxidation to give me that ketone. So then I'll have this methyl group still here with my ketone, should be NaCr2O7, with sulfuric acid and H2O, all in the same all together. So these steps are not separated. The chromic acid is going to be with the sulfuric acid and the H2O. So I have now this ketone, and to form my carbon-carbon bond, now I could use the Gregor reagent, and I'm using I'm gonna be adding a methyl group. So I could use Me for my methyl with magnesium bromide and H2O, and now I'm gonna form a compound with my methyl groups, my original methyl group still in the same position, and now I have an alcohol with now this new carbon bond, which is a methyl group I've been looking for to add. And we know to get from here to here, once again, we have to do a dehydration of an alcohol, which like we did in the last problem, which we could get done with a concentrated sulfuric acid. in heat. And we get to this end problem. Now, there's a few steps in this. So the key point that why we went through most of these steps, and there is another synthesis you could go through for this problem as well, but we'll focus on this one because it deals with the chapter 13 and 14 aspects that are important, is when you see a carbon-carbon bond forming, it's more than likely going to be using of the Grignard reagent, because we don't have many reagents in organic chemistry 1 that form carbon-carbon bonds, unless you're doing a substitution reaction with a cyanide ion, which will add a triple bond with a carbon to your product. So in this case, that was to get to that, to be able to use the Grignard reagent, we had to form a ketone, which is why we went through all these steps to get to the ketone. But once you're at the ketone and you use the Grignard reagent, how easy it is to get to the product. Any questions? Okay. Now, for this synthesis, this is gonna be, we're gonna have to use an epoxide for this, which we see this by the formation of the ether, why we're gonna need an epoxide. So that's like a giveaway. If you see an ether, you're more than likely gonna have to use an epoxide in your reagent, or somewhere in your synthesis is gonna have to be there. So we're gonna have to use the epoxide to form a ring opening reaction. And in this case, the best reagent to use would be acidic conditions with the epoxide tri-substituted to add these two triple bonds as well, because when it's in acidic conditions, the nucleophile is going to attack the more substituted position because of the electronic effects. So you can have an idea what the mechanism of this would look like, because this is the only reagent you would need for this problem. You would have to use this OH of the alcohol is going to act as it's going to function as a nucleophile. So you have your alcohol functioning as a nucleophile, which is going to attack your protonated epoxide, which is another important aspect to remember, that because this is acidic conditions, your epoxide is going to get protonated first. So on the side here, I'm going to draw what this reaction would sort of look like. It would be your alcohol attacking your already protonated epoxide because it's in the acidic conditions, or sometimes the mechanism is going to want you to reflect how this was protonated, which is it took a proton from the acid through a proton transfer. So the nucleophile goes ahead and attacks the more substituted position, which is the tertiary position in this case. So you'll form something like this, with the OH now having a positive charge because it's connected to 3 different parts. And your 2 substituents are going to be there. And when this attack, the nucleophile attacked this, the rings opens by taking, by moving the bond to the oxygen, to your other oxygen. So now this oxygen will be neutral. I'm sorry, I missed one of the carbons. So it'll be these 2 carbons, this carbon, and then in the middle, and then your oxygen connected over here with the OH already on it. because it was protonated beforehand. But now instead of this OH being positive, it's neutral, and your original alcohol is gonna have the positive charge on it. So to get it to become neutral, you're gonna need to use H2O, which is in your reaction from the sulfuric acid to deprotonate the compound, giving you that final product. So that's why this is the only product this is why this is the only reagent you need, because this is what that mechanism is looking like. Any questions? This was the more newer material, so I don't know if there's any questions regarding that. Okay. So it's and it's really important to take from this, especially if you're not too familiar with epoxides, is that how epoxides differ in acidic and basic conditions. So in acidic conditions, it's going to attack the more substituted position as opposed to basic, where it's going to, yes.
Where do the OH and the
What, this step?
No, I mean the on
Here?
Yeah.
So when the alcohol attacks as a nucleophile, the epoxide's protonated because it's in acidic conditions. So the OH is already on the epoxide, but it's just positive. So when it attacks there,
Also, alright, so it doesn't attack the oxygen, it attacks the tertiary.
the tertiary position, yeah.
And it opens.
And then that's why it opens, yeah. And then that's why it goes from being positive to neutral. But this step of being protonated, you're only going to see in acidic conditions. You won't see that in...
Yeah. So the oxygen or the ether over there, it's from the oxygen out.
Yes, exactly. Which got deprotonated because now the positive charge got moved over here. So you needed the H2O to take off the hydrogen, because you're not going to want your molecule to end with any of those positive charges or as well as negative charges. Okay, so now next, here our carbon skeleton is changing, and at some point I dropped my blue pen. Okay. Our carbon skeleton is changing. As well as we're getting introduced to OH groups, so it's going to become an alcohol. So we're going to have 2 OH groups added. So in order to get to that, we don't really know any reagents that will go ahead and add 2 OH groups and a carbon at the same time, but we definitely know a reagent that could add an OH group and form a carbon-carbon bond at the same time, which is that Gregor reagent, because it creates an alcohol and it's gonna add the bond to it at the end. So to get there, there's 2 ways we could have a Gregor reagent attack, and it's a ketone, or it could attack an epoxide, which in this case, it's more likely going to be the epoxide because it will become more efficient. So first off, we need to add a functional group to this starting material so it could be more reactive. So we could do that by adding allylic bromination, which is going to be bromine with heat, which will give us this as our product. And because a new chiral center was formed, but there wasn't one before, this is going to be a racemic mixture. So that's why we're not going to go ahead and put it on a bond, on a wedge or a dash. Now, if our end goal is to try and somehow form an epoxide, then we're probably going to need to form a double bond. So we can eliminate that bromine with NaO ET to have an elimination product, which will give us the product here, as well as tert oxide could have been used for this as well. So then, if we want to introduce an epoxide, we could do so just with having that double bond by using MCPBA, which would give us the preparation. Here we go. This will be the preparation of an epoxide. And I'm going to go ahead and label the other reactions that will happen, just so you're tracking what's going on. So this is an elimination, and this is an allylic bromination, in case you didn't catch when I said that. So now that we can introduce an epoxide to our double bond, it's going to go ahead and form with the double bond. So it's going to form there. So that's going to look like this. With now that tricyclic system, with that epoxide system on forming from the double bond from each side. And once again, this is going to be a racemic mixture, because it could happen on either side. Now, we could go ahead and introduce our, we could use a Grignard reagent to add that carbon-carbon bond. And we're here, relative to this position right here, we're adding in relative to this position, which is where the nucleophile would attack, we need 3 new carbons. So we're gonna need a proper our Grignard reagent to reflect a propyl group, which could be designated with PR. And then it's gonna, which is this is propyl magnesium bromide, and then it needs to be followed by H2O. So then when this happens, it's gonna look like this, with now the OH here, the OH here, and then our propyl group that was out of here. See, 1, 2, 3. So just so it's clear what happened, when the ring opened, when this attacked, the OH gets here, which that becomes an OH because it's protonated by the H2O, and the carbon gets added to this side of the epoxide, which is why we have now the introduction of 3 new carbons, which is what we're looking for. But we still need another oxygen introduced into this problem. So we can actually now form a double bond by dehydrating the alcohol with that concentrated sulfuric acid and heat. Should give us here 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then lastly, if we want to add 2 alcohol groups and an anti-position, we could do an anti-dehydroxylation. Which uses the reagents MCPBA and then H3O plus to protonate both of the alcohol groups. Now, and like I said, this is going to be in an anti-fashion. That's one of the addition reactions we learned back in like chapter 8 or 9. Now, the reason why we couldn't just skip to adding the two OH groups back when we were over here is because we wouldn't have added as well that change in the carbon skeleton. So that's why that we had to go through that, forming the epoxide to add the Gregor reagent and elongate the carbon skeleton. And I want you guys to note that if you've noticed, this concentrated sulfuric acid with heat is actually a pretty useful reagent. It's been used in almost all of the synthesis problems because you could go ahead and dehydrate the alcohol straight to the double bond without having to change it to the good leaving group, which usually makes the problem more efficient rather than changing it to like a tosylic group. Now here we're going from an alkane, a cycloalkane, to an alkane with two bromine groups introduced. So we're gonna add now two bromines. But we're not changing the carbon skeleton at all. And we definitely know a reagent that could add one bromine, but we don't know them both at the same time straight from an alkane. So we're gonna have to just add the first one to be able to get the alkane functional. And because this is a symmetrical cycloalkane, you can actually use either radical chlorination or radical bromination. So CO2 would be just as correct as using of Br2 with heat or light. So then, and like I said, because it's symmetrical, it's not going to be selective, so it could go anywhere, but I'll stick to using bromine. So once I get my bromine, if I know a reagent that could add the two bromine groups at the same time, but I'm going to need a double bond to do that, so I'll perform an elimination reaction to form a double bond. And because there's no substituent groups or anything, and I'm not worried about whether I get the Huffman or Zaitsev product, I could go ahead and use terbutyl oxide with potassium because I want a strong base that I know is going to go through to an elimination and is not going to give me any substitution products. So first I went ahead and did a radical chlorination. Bromination could be used in this case. And then here, elimination with a strong base. Oh my gosh, my spelling. Elimination with strong base. And then from here, we could just go ahead and do a bromination reaction straight to it because that's going to give us our anti-addition anyways, and that's going to be Br2. So here we did bromination. And it gave us our anti-addition. And if there's any parts of reagents that you actually have to have more memorized than other parts, is knowing the stereochemistry of it and why. Because if you notice, sometimes it's going to be the stereochemistry is its way because it formed a ring, and other times it's just because it decides to attack on other sides. So that's actually an important concept to understand. Rather than the actual reagents being used. They're just as important, if anything. Now, moving on to problem 15, since we did a lot of synthesis problems. This is going to go back to resonance stabilization. So here, it's asking which compound has the greater resonance stabilization. So greater is when dealing with resonance means which has more significant resonance structures. And also more than anything, how the charges are reflected on the resonance structures. So where are your positive and negative charges? So if that's said, you could either go ahead and like pick which one you would want to look at the resonance more, or if you're really familiar with how things are like positioned. But like for instance, I know that when these two groups are opposite of each other in this way, are completely opposite of each other, opposed to these that are only this group that's 2 carbons away, this one's on the complete other side of that benzene ring, that I could have a resonance structure that moves the charge up here. Then I could go ahead and even move this bond over here, because now that space would be open. And consequently, when this bond moves, because it's a benzene ring where the resonance is completely within it, you can move this bond over here, and I have my lone pairs here, so now that bond's moved there. So the resulting resonance structure would look like this, with now a double bond formed there, a double bond formed from the oxygen, and now I have a positive charge on my oxygen. So that's what this resonance structure would look like. As opposed to if I did the same concept that I did on this structure as I did over here, then I can move my negative here, move this bond here, and then once I move this bond as well here, instead of this bond being able to move now onto the oxygen and create a double bond there, it still can't do that, because there still won't be there won't be space for a double bond to be formed here, because then that will violate one of the rules of resonance by going over the structure. So all I could simply do is move that here, which won't change what my charge on my oxygen atom would be, because this would be the resulting of that. With now my positive on a carbon. This, giving this product the greater, the compound B in this case, if you want to name this one B and this one A, the greater resonance structure, because it has that resonance structure that compound A lacks by having an oxygen atom with both the negative and the positive charge on it. So once again, this would be the greater resonance. This compound will have the greater resonance stabilization, because you're localizing 2 charges on 2 oxygen atoms as opposed to an oxygen and a carbon atom. Now, this problem is dealing with the most acidic proton. So first off, you'll look at where your different protons are. So like I know I have protons here relative to my ketone. I have a proton here. I don't have any in the middle there. I have 2 here, another 2 here. I have 3 over here, and 2 more here, 1 here. And you could keep going through all this, especially if you're not familiar with where the most acidic proton is. But rather than drawing out where all the protons are, you can go ahead and look for certain key parts of where the more acidic will lead to. So we know we're looking for a more acidic proton. That means that our deprotonation of the most acidic proton will lead to, you're looking for what leads to the most stable conjugate base. Acidic proton to most stable conjugate base. So when looking for that, we know a conjugate base could be stabilized by induction effects, which here we don't have any electronegative atoms in, other than this oxygen on this carbonyl group. But we don't have no chlorine or fluorine to bring in those induction effects as well. So we'll have to stick to the resonance stabilization, which we do have. So from that, when looking at what when which proton is deprotonated, what will lead to a more electronegative atom, you'll look for again those resonance patterns. So when this proton, which is in an allylic, which is relative to this pi bond, gets deprotonated, it'll go ahead and give you a negative here, which can then be resonance stabilized by this bond moving over here, and as well can even, you could then create, you could move it over here. I'm trying to see, I'm just gonna draw it off for you guys. So when this double bond is moved here, so let's say that a proton was just deprotonated. That's a carbon, not an oxygen up there. Now it has resonance stabilization from this being able to move over here and this being able to move over here, and this will give the negative on the oxygen now. So now you have, you're able to delocalize that negative sign on the carbon atom and the oxygen atom as well. And with that, that makes it the most acidic proton because of that resonance stabilization, opposed to the other protons that won't do that in that way, such as this one in the vanillic position, that you won't get resonance stabilization there, or over here, it won't be as a profound effect. This would have the most resonance stabilization. So once again, when you're looking for the most acidic proton, look at how when it's deprotonated, how it affects the conjugate base, because the more acidic, the stronger the acid, the more stable the conjugate base. Now, moving on to a nantometric excess problem, especially that I know Professor Yuan likes to incorporate in his exams. Here, we're given the specific rotation of both the S enantiomer and the R enantiomer, and then we're looking for which isomer is going to be dominant and what the optical purity would be of the mixture. So we know an equation that could find that. And first off, before anything, we could actually already figure out without calculating anything what the more dominant enantiomer is by looking at the specific rotation of the mixture. So because the specific rotation of the mixture is positive, we know that the dominant enantiomer is going to be, in this case, the S enantiomer. Just as well as if it was a negative specific rotation, then the more dominant enantiomer would have been the negative, the enantiomer with the negative specific rotation, which would have been R. But it's going to be positive for this case. So our dominant already is going to be S. And then our equation for optical purity percentage is going to be 100 times the absolute value of the specific rotation, which I'm going to denote with A. So here, A equals specific rotation. Of the mixture divided by the specific rotation of the pure sample. And so we plug in the numbers that we have, which would be 100 times our mixture is going to be this number, the positive 11.2, divided by, and our pure sample, we're going to use the dominant enantiomer, which is going to be the S enantiomer, so it's going to be positive 43.2, which is going to give us around 26%. This same method could be used if the question was asking what is the excess of the dominant enantiomer over the non-dominant enantiomer, because this 26% signifies that there's a 26% excess of S over R. So when it could have answered either of those questions. The question could be worded multiple ways, and you could have used this equation to answer it. Yeah.
So 11.2 was the specific rotation, the S enantiomer?
It's the specific rotation of the mixture. So because it said what is the optical purity of a mixture, and then that's why it says the 11.2 degrees, the positive 11.2 degrees. We know that's already the mixture, which that's not going to change. What's the important part, especially when finding what the excess would be over, because even though it's absolute value, you get away with putting either one of the numbers, but it'll get messed up. Your answer will get messed up if it's asking what's the dominant or what's the excess. So you compare the specific rotations sign with that of what the dominant enantiomer is.
The optical purity percentage accounts for 11. What is it exact? So
Yeah, so it also, it can, knowing the optical purity can also tell us what's in excess of what. In this case, which is saying there's 26% excess of S over R. Any other questions? Okay. Now here we're just identifying arrow pushing patterns. So here, even though there's two arrows, which is signifying like making space, it's a nucleophile attack, because this H2O is going to act as a nucleophile and attack that electrophilic center. That's being this center becomes electrophilic because this carbonyl group and the oxygen on the carbonyl group is pulling the electricity that way, making this partial positive, as well as that chlorine also is also helping make that even more partial positive, and making it an electrophilic center. Then here, this will be the loss of a leaving group, because the chlorine's being lost, as well as now again this bond is being reformed. So this is, but more than anything, it's a loss of a leaving group. And here, now the H2O, which was being used as a nucleophile before, is being used as a base to extract that proton. So it's gonna go ahead and do a proton transfer. Giving us our resulting carboxylic acid. And back here, this is asking what is the rate equation of the following reaction. So with this problem, more than anything, you have to know what type of reaction is going on, and then be familiar with your unimolecular and your bimolecular and how those compare to substitution and elimination reactions. So one of the giveaways here is we know this is going to be a substitution because our leaving group is just being replaced by the nucleophile. So through there we know it's that sort of tells us it's going to be a substitution reaction. And then some other key things to notice is that you're getting inversion of your configuration from your starting material to your end material. Your inversion of your configuration. Then this is a good nucleophile because you're gonna have electron density with once that spectator ion leaves. You're gonna have electron density on that oxygen because of that negative charge. So you're gonna be readily able to give electron pairs. So this is acting as a good nucleophile. And your substrate is secondary. So their substrate being secondary could be for either SN1 or SN2 reaction. So that doesn't really tell us between the two. And it being a good nucleophile is preferred for SN2, but it can also be used with SN1. But more than anything, what's giving us away here is an inversion of configuration. So we know this is going to be an SN2 reaction because the nucleophile is going to attack from the backside, which inverts the configuration. So now from this is just remembering what the rate of a SN2 reaction it looks like, which is going to include both the substrate and the nucleophile in it, not only the substrate. And the names of these molecules, for instance, would be sodium acetate. And if we go ahead and find the name for this, it would be, let's see, we would start numbering from this side because it'll give us a smaller substituent. So this will be 1, 2, 3, 4, 5. That's going to be a pentane group with 3 bromo, 2 methyl, and our configuration would be 1, 2, 3, and then our H on the back we'll get 4, and that's going to be clockwise, so it'll be R. So they could give it to you like that to name it, giving you the rate, but it still doesn't change that the rate would include both the sodium acetate and the R3 bromo 2 methyl pentane with K. And now lastly, this question is asking you to predict the products of the following reaction, which this is from chapter 14. So here, once you see that MCPBA, you already know you're going to have an epoxide form, whether it's going to give you that dehydroxylation, that anti-dehydroxylation, or you're just needing the epoxide form to continue with a reaction to allow the nucleophile to attack. So first off, I'll go ahead and draw my epoxide being introduced, which is just going to form from the double bond. And now with this, I generated an epoxide, which is going to be race mixture because the chirality center was formed. Or because there wasn't chirality. So this is going to be race mix, which now allows me to introduce a nucleophile to attack at the less substituted position, because this is going to be the H2O gives me more basic conditions than acidic. So when my nucleophile attacks, I'll end up with this product, because my nucleophile would attack here at the less substituted position, so the SH will get attached there, and then at the end, even though this is going to be this will end up in an ion, it's going to get protonated by the H2O, which is why this H2O part is important. Usually if you see an H2O after in a reagent, it means it's because it's making sure that protonation goes through, which is going to give you that alcohol versus the alkoxide ion. So that's the end of this review. Is there any questions regarding any of the questions I went through that you maybe want to make sure understand again? Okay, if you didn't get a survey coming in, please grab one and fill it out really quickly. It takes like a minute, or turn it in if you did get one, because that really helps Study Union how they conduct these reviews. And if there's any questions that you want to ask me, I'll be here until up here. I'll be here until about 11:55, because we have to end the session a little earlier to make sure everybody could get in. And good luck on your final, everyone.